Have you ever stopped to think how, your data actually gets from A to B? Like a video stream or just a quick message online, crossing huge networks almost instantly. It seems like magic, but it's actually some seriously precise traffic management working behind the scenes. The thing is, with everything exploding, AI, 5G, IoT, the old ways, are starting to show their limits. So today on the Deep Dive, we're getting into something pretty revolutionary that's tackling exactly these challenges: segment routing. We're going to unpack how it's changing the game for directing network traffic, making things faster, way more flexible, and tougher for what's coming next.
Yeah, and for this one, we're looking right at the source code, so to speak. We've got the foundational RFCs, that's request for comments like RFC 8402, which first laid out the segment routing architecture back in 2018. And then there's its powerful follow-up RFC 9256 from 2022, which dives deep into segment routing policy. We also have some great real-world perspective from Nokia, showing how this stuff actually works in practice and what benefits people are seeing.
Okay, so our mission today: cut through the tech speak, pull out the really key ideas, and give you a solid handle on this major shift in networking. Ready to jump in?
All right, so before we get lost in segment routing itself, maybe let's just quickly paint the picture. How does data normally navigate a big network today? Like, what's the standard approach?
Good starting point. Think of it like a huge road network. Traditionally, protocols like OSPF, Open Shortest Path First, have been the workhorses. With OSPF, every router, like every intersection, keeps its own map of the entire network area. It's called a link state database. This map shows all the connections, maybe how busy they are, who the neighbors are.
So each router is kind of figuring it out on its own.
Exactly. Based on that map, each router calculates the best or shortest path from its location to every possible destination. This forms its local routing table, its personal set of directions. And to keep these maps up to date, routers constantly chat with their neighbors, sending out little updates, link state advertisements, or LSAs whenever something changes, like a road closure or a new highway opening. That sounds dynamic, but maybe a bit chatty.
It is dynamic, and that's been key to the internet scaling like it has. But yeah, all that constant calculation and communication across potentially thousands of routers, it introduces complexity and sometimes limits how quickly the network can react or how precisely you can control specific flows.
Okay, so OSPF is like this distributed intelligence, everyone figuring out their own best way.
Yeah.
How does segment routing flip that? You said it redefines control.
It really does. Segment routing, or SR, takes a fundamentally different approach. Instead of each router making independent decisions hop by hop, the entire path is defined right at the beginning, at the network entry point, the ingress router. The core concept, right from RFC 8402, is about establishing predetermined deterministic paths.
Deterministic meaning predictable.
Precisely. And it does this using segments. Think of segments as specific instructions attached to the data packet itself. These could be MPLS labels or, in IPv6 networks, even parts of an IPv6 address. Each segment essentially tells the packet, okay, next, go through this specific node or take this specific link. So the analogy shifts, instead of every car asking for directions at each junction.
It's like putting a detailed itinerary on the package before it even ships, specifying every single stop and turn.
Exactly that. You pre-plan the entire journey. The intelligence needed to figure out the path is concentrated at the edge or by a central controller.
Okay, so if the planning moves to the edge, does that mean the routers in the middle, the core network, get simpler?
That's one of the huge advantages. It significantly simplifies the core. And pulling from the Nokia material, this leads to real benefits. First, scalable traffic engineering. Because intermediate routers don't need to hold on to as much temporary routing information, what we call soft state. You reduce the demands on their memory, their processing power, even the network bandwidth used just for signaling routing updates. It streamlines the whole operation.
Makes sense. Less thinking for everyone in the middle.
Right. But it's not just about making things leaner. SR unlocks new revenue streams. Because you have this precise control, service providers can create things like dedicated, guaranteed network slices. Imagine a slice with guaranteed low latency end-to-end, maybe for financial trading or remote surgery. Or a slice optimized for massive IoT data. SR makes building and managing these transport network slices much more feasible.
Wow, okay. So it's efficiency and enabling totally new kinds of services. That feels like a really big deal.
It absolutely is. And the mechanism for defining these sophisticated paths is SR policy, which RFC 9256 really fleshes out. And SR policy isn't just about one path from A to B. It actually defines a source, a destination, and potentially a whole set of candidate paths between them, each with different characteristics or purposes.
A set of paths. Like options.
Exactly. And these candidate paths are carefully identified. They have attributes like protocol origin value, telling you how the path was learned. Was it configured manually, learned via BGP, or from a controller like a PCE? They also have an originator identifier, basically, who define this path, and a unique discriminator value, like a serial number, for that specific path within that policy. This helps the network choose and manage these paths precisely.
That sounds incredibly granular, almost like having different preset plays you can run for your traffic. Are these paths rigid, or can they change?
Both. That's the flexibility. You can have explicit candidate paths. These are laid out step by step, often by an operator or a controller. Think of them as fixed engineered routes for critical traffic, or maybe a backup path of last resort. The main router just needs to check if the path is valid. Then you have dynamic candidate paths. These are calculated maybe by the head-end router itself or by that external path computation element based on current network conditions. And crucially, they can be recalculated if the network changes, if a link goes down, for instance.
Okay, explicit for predictability, dynamic for adaptability. How does the network actually steer traffic onto one of these specific policy paths?
That's where the binding SID or BSID comes in. This is super important. A BSID is a specific segment identifier like a label or an address that acts as a unique handle for an active SR policy path. When a packet arrives needing to follow a certain policy, the ingress router slaps on the corresponding BSID. That single BSID then tells the network exactly which complex multi-step path to follow. It makes steering traffic onto these potentially complex paths really efficient.
Got it. So the BSID is like a shortcut code that points to a whole predefined journey. That seems powerful, especially thinking about, well, when things go wrong, network resilience.
Absolutely. Resilience is a core benefit. RFC 9256 points out how SR policies work hand in hand with protection mechanisms like TI-LFA, topology independent loop-free alternate. TI-LFA provides really fast local protection. If a router detects its immediate next hop has failed, TI-LFA lets it switch to a pre-calculated backup path in like under 50 milliseconds, often seamless to the application.
50 milliseconds. That's
Yeah.
incredibly fast.
It is, and SR policy can enhance this. You can even configure an SR policy specifically to act as a backup path for a particular link or node, maybe for situations where standard TI-LFA doesn't apply perfectly. And to detect failures that quickly, networks often use BFD bidirectional forwarding detection. Think of it as a super fast heartbeat check between routers. If the heartbeat stops, BFD tells the router almost instantly, triggering that fast switch over to the protected path defined by TI-LFA or an SR policy.
So you've got the best path and an almost instantaneous backup ready to kick in. That's critical for anything that can't tolerate downtime, which is, well, most things these days.
Pretty much everything, yeah. Now, it's also worth noting that segment routing isn't just one single thing. There are different ways to implement it, different flavors. The main two you hear about are SR-MPLS and SRv6. SR-MPLS uses the existing MPLS framework. The segments are standard MPLS labels. Many networks already use MPLS, so this can be a smoother evolution for them.
Okay, leveraging what's already there.
Exactly. Then there's SRv6. This is really interesting because it builds segment routing capabilities directly into IPv6. The segments are actually encoded within the IPv6 address space itself, using extension headers. This avoids needing a separate MPLS layer and takes advantage of IPv6's flexibility. RFC 9256 actually details a bunch of different segment types for both SR-MPLS and SRv6, showing how you can represent nodes, links, BGP peering relationships, all sorts of things as segments.
And these aren't just lab experiments, right? You mentioned Nokia.
Right. Nokia explicitly states their SR-MPLS and SRv6 solutions are built on extensive global deployment experience. They talk about supporting seamless network evolution. So yes, this technology is definitely out there running in real, large-scale networks.
Good to know. So beyond the core path definition and resilience, what other advanced tricks can SR do?
Well, building on that precise control, you get constraint-based forwarding. This means you can program paths based on more than just the shortest route, need a guaranteed low latency path for, say, cloud gaming. SR can help engineer that. Worried about data sovereignty? You can constrain traffic to only flow through routers within a specific country or region. This can be combined with things like IGP flexible algorithms, letting you optimize paths based on custom metrics, maybe minimizing energy use or avoiding certain types of links.
So optimizing for different business or technical needs, not just speed.
Precisely. Another one is peering engineering. A router at the edge of your network can use SR to very specifically choose which link to use when sending traffic to a neighboring network, like your internet provider or a partner network. great for load balancing or ensuring traffic goes via a preferred peering point. And finally, it integrates tightly with BGP, the protocol that runs the global internet. You can use SR policies to influence BGP routing decisions in very sophisticated ways, managing how traffic enters or leaves your network across multiple connections.
This paints a picture of a network that's way more programmable, intelligent, and proactive rather than just reacting to links going up or down.
Hmm.
Okay, so we've really covered some ground here. We started with that traditional OSPF world, where intelligence is distributed, and journeyed into segment routing, where path control is much more centralized and pre-programmed. It seems clear from this deep dive that SR really does offer this step change in control, in scalability, and importantly, in resilience for the kinds of networks we rely on now.
Yeah, I think that's the core takeaway. Moving path definition to the ingress using these concise segments, it simplifies the network core, speeds up recovery, and crucially, it enables these new, innovative services like network slicing that just weren't practical before. It feels like a truly foundational shift.
So thinking about all this, what really stands out to you listening in? For me, maybe it's this idea that the journey your data takes is becoming less about just finding any available path and more about following the specific engineered path that's best suited for its purpose, whether that's raw speed, low jitter, or security. And looking forward, it makes you wonder, right, how will this balance between distributed logic and this kind of centralized programmable control continue to evolve, especially with demands from things like AI and the metaverse just around the corner? What new possibilities might that unlock for global connectivity? Lots to think about.